Good morning, students. Today we are going to talk on elastic properties of materials. These are the reference and textbooks which are already told in the class. This is the syllabus of module 2. In that, up to module 2.2 it is completed earlier. 2.3 and 2.4 which I am going to cover in this slides through online teaching in the Zoom platform, and also this information will be shared in Google Classroom and YouTube video also. So 2.3, that is bending of beams. In that we will discuss about definition of beams, different types of beams which are available, and we derive the expression for bending moment in terms of moment of inertia, and we derive the expression for Young's modulus or the depression for a rectangular beam of cantilever case. And in 2.4 topic we will discuss about torsion of cylinders. In that heading we have twisting couple per unit twist for a solid cylinder, and applications of this torsional pendulum. These are the two topics we are going to cover under 2.4 section. So 2.3, where bending of beams. First you should know what is a beam. A beam is a rod or a bar of uniform cross section of homogeneous isotropic elastic material whose length is very large compared to its thickness. Isotropic means where it is direction independent. Here the physical property, that is elastic property of a material, is independent of direction, and the beam is uniform. When you subject the beam to a load, say here example in figure A, E to F, which is called a neutral axis or a natural axis, that axis will not going to change its length or its dimension under the load, but above this particular section which gets expand because of the extended force outside, and below this EF which gets contract, that we'll see in the next section or in the next slide. So before understanding this, you should know some of the terminologies here. Those terminologies are, if this is the bar, in the middle of this bar you have EF, that is the natural surface, natural axis, and the surface associated with which is perpendicular to the plane ABCD, that is called natural surface, and ABCD is called the plane of symmetry and bending, through which the bending which occurs at all the different planes. Above EF, all the planes which are in AB line get expanded, and below this EF point which are near to DC gets contracted. In this, the outermost surface, that is AB, which gets expand maximum, and in the downside the lowermost layer, that is DC, which is going to contrast to the maximum. Here the axis of bending is along this PQ plane. There are different types of beams which are available, such as cantilever, where one end is fixed, other end is free to apply load. Simply supported beam, where both sides it is supported with supporters, and you can apply the load at any point between these two fixed supports. Overwhelming, where you can change the position of both the supports. Continuous, where one end is fixed, other ends continuously at different intervals. You can apply, you can give the support and load can be applied anywhere. This type of thing you will see it in the bridges. Fixed end means both the ends of the beam is fixed and you can apply the load at any point based on that load, how much you apply and where you apply between these two supported ends, the extension of bending will be different. And the first case cantilever, and F the cantilever, where the load is applied at the end, that is called a simple cantilever or simply supported beam. These are the different types of beams which are available. About these you will study in civil class also. in more detail, where you will going to study the force of action and how that force makes the beam to bend. That you will study it in the civil class in more detail. For physics class, only the naming and their diagrams of different types of beams is sufficient. The next topic is you have to determine the bending moment of a given bar. So we will take the case of cantilever, which is there in figure A. The cantilever which is fixed at one end and the load is applied on the other end at point F. At E point or A to D, AED, that plane is fixed, whereas BFC, where the load is applied. Let us consider a cross-sectional plane PP dash across which the load is applied and equivalent opposite weight it is going to act, and that lead to a bending in the beam. So this bending in the beam will not change the dimensions of the natural axis or neutral axis EF, whereas above this EF all the planes like AB or any plane between E to A or F to B, they are going to expand. Similarly, between E to D and F to C, they are going to contract. We will take one of the case, that is only the expansion case. For this figure B, if you observe figure B, where the cross-sectional view of the beam is observed with arcs, and then you can consider the center of curvature for these arcs. From the center of curvature, if you draw the lines to get the radius of curvatures for the neutral axis EF and for the extended axis AB, then they cut the neutral axis and the extended axis at AB and A dash B dash. Since AB is expanded, capital AB is expanded, naturally the small a dash, small b dash, which is going to be more than the small a and small b, because small a and small b is fixed, it was not going to change. Okay, so in that way the explanations are given here. Now arc lengths we can determine with the help of this simple geometrical diagram. The arc length AB can be determined as the radius of curvature of this is capital R and the angle subtended by this arc is theta, because the angle, the definition of angle itself, it is arc by the radial distance. So AB is the arc and the radial distance is OB. Therefore, if you want the arc length AB, it is simply capital R into theta. Similarly, for A dash B dash, which is extended from B to B dash, where B to B dash or A to A dash, that distance is taken as Z. Hence, the radial distance for the arc A dash B dash becomes R plus Z into theta. Hence, arc length A dash B dash is R plus Z into theta. Okay. So now, based on this, the increase in length of them is given by A dash B dash minus AB, that is R plus Z into theta minus R theta, where R theta get cancelled, you left with Z theta. This is increase in length or change in length. To determine the strain in this cantilever, let us consider the definition of strain. Strain is equal to change in length by vertical length, that is Z theta by R theta. Theta get cancelled, so you left with Z by R. As you know, the strain is proportional to this distance from the natural axis or neutral axis. Now consider a small area which is going to create with AB a line element in that plane. So delta A is a small area at a distance Z from the neutral axis. Then from the definition of Young's modulus is equal to stress by strain. Therefore, stress is equal to Young's modulus into strain. Stress is nothing but force by area. Therefore, F by delta A, where delta A is the area, which is equal to Young's modulus Y into strain. strain is Z by R from the previous expression. Therefore, you get an expression for force as Y Z delta A divided by R. To determine the momentum, the definition of moment of force, it says that it is the force into the perpendicular distance to the plane. Hence, force is Y into Z by R into delta A, and perpendicular distance to this plane is Z. So, the moment of this force is Y into Z square delta A by capital R. To determine the total moment of the force acting on all the filaments in that particular plane, then you need to take the summation. That summation leads to summation of Z square into delta A by taking Y by R as constant. Here, summation of delta A into Z square is analog to the moment of inertia. Moment of inertia is mass into the radial distance square. Here, instead of mass, we take a area. Hence, area into the radial perpendicular distance square, that is delta A into Z square of all summations, which can be called as geometrical moment of inertia, noted as Ig. So, the geometrical moment of inertia Ig is equal to summation of delta A into Z square. Equivalent to that, you can write it as the resultant area A into the resultant radius of gyration, that is K. In terms of K square, you can write, where radius of gyration is the imaginary axis which is equivalent to the moment of inertia of all the masses and their squares of the radial distance. So, instead of masses, here all the small section area of cross sections into their radial distances, perpendicular distances from the axis. So, just K value, if you substitute there, the moment of forces is Y by R into Ig. This is called the restoring couple or the bending moment of the beam. Ig, that is the geometrical moment of inertia for a rectangular cross section, you can write it as area as breadth into thickness, and the moment of the radius of gyration square, that is K square, is D square by 12, where D is thickness of the beam. So, these are known things, you no need to derive them separately. Let us consider them as a known equations. Then the expression for Ig becomes BD cube by 12. Therefore, the bending moment of for a rectangular cross section, it becomes YBD cube I whole divided by 12R. So, this expression, it is important, and this derivation will be generally asked for 6 to 7 marks, which is important. We will move to the next topic, that is the cantilever. As you know, the cantilever is a beam again which is fixed at one end, and at the other end the load is acted, making the length of the beam to change along its axis. So, we have to derive the expression for depression of a single cantilever in terms of Young's modulus, or you can derive the expression for Young's modulus of a single cantilever in terms of the depression due to the load which is applied, the load of W which is applied to the beam along its length. Let us consider the weight of the beam is ineffective here, mass or weight of the beam is not so high. Let AB be the natural axis of the cantilever of length L as shown in the figure. It is fixed at one end and it is loaded at another end, that is at B point with a weight of W. Then the end B is depressed into a position, new position B dash, and the natural axis takes up the position AB dash. Consider a section P of the beam at a distance of x from the fixed end A. Then the bending moment is W into PB, where PB is nothing but L minus x, because total length is L, in that A to P is x, therefore P to B is L minus x. Since the beam is in equilibrium, we can write this beam moment from the previous derivation, that is Y by R into AK square which is equal to W into L minus X, where R is the radius of the curvature. Now let us consider one more point Q, which is very close to P at a distance of dx from P. Now PQ is the distance which can be expressed with an arc. So PQ is considered as an arc which can be expressed as radius into the angle subtended by this arc. Therefore PQ, which is a small distance dx, which is equal to R into d theta. Therefore then R, that is the radial distance, can be expressed as dx by d theta. Then the equation 1 changes into W into L minus X, which is equal to Y by R into Ig, which is equal to Y d theta by dx into AK square, where we substituted the value of R as dx by d theta. From this equation, just by rearranging, you get d theta equal to W into L minus X into dx divided by Y into AK square. Now the depression of Q below P is equal to CD. From the diagram you can see that CD is equal to dy, that is small change along y axis. Then dy is equal to L minus X into d theta. Therefore dy is equal to L minus X into W into L minus X into dx by Y AK square, where L minus X 2 times it is there, therefore it gets multiplied, that is it becomes square. Then W into L minus X whole square into dx by Y AK square. Now the total depression Y you can calculate by integrating from 0 to L the dy value. Then by integration, here before integration you can expand L minus X square as L square plus X square minus 2LX, which is same as A minus B whole square. A minus B whole square equal to A square plus B square minus 2AB. Here we are integrating this equation with respect to X, and W, Y, A and small a and K squares are constants. You can take them from the integration sign. By integrating L square with respect to X, so it is L square into 1. So integration of 1 is X. Therefore you get LX square, XL square as the first term. Second term, X square, when you integrate with respect to X, it becomes X cube by 3. And the third term 2L is constant. Integration of X is X square by 2. Now substitute the limits 0 to L. By simplifying you get YL cube by YIG into 3YIG. For a rectangular cross section, you can write the IG value as BD cube by 12 as you seen in the previous derivation, and you can write the weight W as mass into acceleration due to gravity. So W equal to mg. Then the expression for Y changes to 4mgl cube by YBD cube. This is what the expression used in the lab also for determining the Young's modulus of a single cantilever, where small y is the depression and capital Y in the right side is the Young's modulus. If you know the depression from experimentally, then you can find the Young's modulus of a given material. For that you need to change the capital Y and small y positions. Or if you know the Young's modulus of a given material, then you can calculate the depression at different places. At the end where the load is applied, you can calculate. If you want to calculate the depression at any other point other than at L, then you must change the integration limits from 0 to L to the value of L instead of L exactly at the middle. If you want to find L becomes L by 2, then you need to integrate separately and then simplify to get the depression at any point on the single cantilever. Okay, hopefully this is one more important derivation which is asked most of the time in many of the previous semester exams, even in internal tests. Hence this derivation is also important in this chapter. Next, one more, the last topic of this particular chapter is twisting couple on a cylinder or a wire, a cylindrical wire. So let us consider a cylindrical rod of length L as shown in the diagram and radius R and a coefficient of rigidity as Y or eta, we generally take it. its upper end is fixed at 1 and the couple is applied in a plane perpendicular to its length at a lower end of the figure A. So when you apply a perpendicular to the plane, then there will be a twist. You can consider many of the cross-sectional areas of a circular, just like circular plates arranged one above the other, in which the last one, if you take where O dash A, which is not going to change because it is fixed end, whereas OB, before applying the twist or the force, it changes to OB dash with an angle theta after applying the load. That means B to B dash is the change in the twist, the point B with respect to the earlier position. Now you can join A with B and B dash, you get one more triangle, that is ABB dash. Let us consider the angle subtended by this, that is BAB dash angle is phi, and consider BOB dash as theta. Okay, so shear stress by angle of shear, so shear stress is F by F, that is force per unit area, by angle of shear is phi, then F is equal to eta into phi or eta into x theta by L. The surface area of this hollow cylinder is 2 pi x into dx. Therefore, the total shearing force on this area is 2 pi x dx y into x into theta by L. With simplification, it will change us into 2 pi y, where capital Y is Young's rigidity modulus. It is not y, it is eta. I'm going to change that y to eta. Then x square theta into L into dx. The moment of this force is 2 pi eta x square theta by L into dx into the perpendicular distance, that is x. Then it changes into 2 pi eta x cube theta by L into, from the exam point of view. So, and numericals on this topic is also important. The small subtopic of this same thing, you can consider the torsional pendulum. Torsional pendulum is one where one end is fixed, the other end is a wire which is taken, and the other end of this wire is loaded with a rigid body. So the rigid body is one which will not going to deform easily with the small forces. So such type of uniform or irregular rigid bodies you can attach with the help of check nuts, and you can find the time period associated with this. So here, to find the time period associated with this torsional pendulum, let us consider a heavy cylindrical rod or a disc which is suspended from the end of the fine wire, whose upper end is fixed, and it is subjected to a torsional oscillation, that is twisted oscillations. Let theta be the twisting angle, then the restoring couple per unit restoring couple is C theta, where C is nothing but pi eta r to the power of 4 by 2L. This particular restoring couple produces an angular acceleration in this, that is d omega by dt in the rod or in the disc. Then the I into d omega by dt is equal to minus C into theta. Therefore, if you want d omega by dt, which is equal to minus C theta by I, which is equal to pi r square, because it's a circular disc, area of circular disc is pi r square. In this equation, I is the moment of inertia of this rod disc. To determine the time period, from the definition of time period from module 1, you know that time period t equal to 2 pi into square root of displacement by angular acceleration. Therefore, t is equal to 2 pi into displacement is theta and acceleration is c by I into theta. Here neglect the negative sign, which is just a sign convention indicates. So by ignoring that, you get the expression for time period of a torsional pendulum as 2 pi into root of I by C, where I is the moment of inertia and C is the couple per unit twist of the given torsional pendulum. Okay, so this is additional small derivation rarely it will be asked, and numericals on this are important. The last small topic of this chapter or the module is applications of torsional pendulum. The working of torsional pendulum clocks is based on the torsional oscillations. The freely decaying oscillations of torsion pendulum in a medium helps to determine their characteristic properties like polymers or any other elastic materials. Determination of frictional forces between solid surfaces and flowing liquids can be determined with the help of torsional pendulums. Torsional springs are used in torsional pendulum clocks and in many other uh, equipments. Uh, Clock pins, which works with the principle of torsional rotation. Similarly, in automotive industries, in many applications for suspension of vehicles, chassis, automotive valves, clutches, gear shifts, there it works with the torsional oscillations. Even in medical equipments, torsional springs are used for the immobilization devices, hospital beds, several dental application, wheelchairs, lifts, etc. Door hinges also, which is working with the principle of torsional oscillations, where the springs are attached, it will come back to its original position.